Okay, so now let's talk about design of built-up sections or analysis of built-up sections. So as we discussed last time, even in a cross section, even in cross section of beam, so we need to consider there exists the shear stress distribution over the cross section. So if you have certain material, so obviously the shear strength of the material must be greater than the shear stress to prevent any failure by the shear stress development, isn't it? So in most of cases, the materials are not tend to fail by the shear stress. Usually the materials would fail, earlier by what the tensile strength typically. But of course, in the case of like high ductility steel, the material, the shear deformation is much more important than the the elongation in the longitudinal direction. But let's consider the built-up sections here. So in this example, in the first example, we have a rectangular section, so made from four different wooden plate here, and here, and here. So to form all the sections together, we need to have what? We need to connect them each other, here, and here, and here. So what? How? The first we may use a glue, 접착제, or we can use a nail, isn't it right? Screw nail, isn't it? Yeah. So what is the role of glues or nails? The role of glues and nails is what? The mission, the jobs of glues and nails to glue all the parts together, isn't it? So which means it should be able to resist the shear stress development or the shear flow development in the cross section. Okay, that's what we want to discuss here. And how about the second example? The second example, so we use multiple layers to build a large wooden section here. So of course, as we discussed in the last time, so we need to check the shear stress development on the individual layers. So we need to check the shear stress. The shear stress should be less than any of the shear strength provided by the glue. For example, in the case of rectangular section, the maximum shear stress developed here, where? In the middle of the section here, isn't it right? So maximum shear stress was equal to 1.5 times the average shear stress value. Okay, so when we design the glue, so we need to satisfy this criterion, otherwise the section would fail by the shear stress development. Let's consider third example. Third example, this is a built-up section of I-shaped section by welding. So we have 1, 2, 3 different plates, and we weld them together. Okay, we weld them together to build a big I-shaped section. So this is called weld or welding. In 우리말 we call, sorry, 용접. Okay, 용접. Okay, let me talk about the welding a little bit more. So let's consider welding, job of welding. So I have a web and a flange. Okay, and then we connect them together by welding. The welding material. And then here I have some shear stress development, isn't it? The resistance provided by this welding is what? For example, some kind of allowable shear strength. And then we need to consider the welding thickness. For example, I want to say the BW, for example, altogether, the BW. This is the shear flow. This is shear flow provided by welding, isn't it? So to guarantee the safety, the shear flow provided by the welding must be greater than the shear flow caused by the shear force, isn't it? That's how we design this welding. And then the fourth example is a rebate connection. So we have, for example, where I have a small member, the I-shaped section, and then this I-shaped section is reinforced by using a channel section, and these two parts are connected together by using rivets. Okay. Then how do you calculate the shear flow provided the rivet? The shear flow provided rivet is what? The probably there exists the shear strength of a rivet. The shear strength, how do they say, the force of the shear or rivet, force of rivet, and we have two of them. And then if you consider the longitudinal direction, then the rivet would be placed in every s distance. Then should be divided by every s distance. This is the shear flow provided by the rivet connection. And then this example that I already explained you. Okay. Okay, so let's consider the example directly. So I have a wood box beam here. This wood box beam is constructed of two boards. The size of each is 40 times 180 millimeters. Its thickness is 40, and then its width is 180 millimeters in the cross section. And then these serves as flanges on top flanges and then bottom flanges here. And then two plywood web, we have web, and each is what, the 15 millimeters thick. The 15 millimeters thick. We have two plates here, and they are connected together by using a screw nail. So we have wood screws, and then we connect them. The allowable load of provided by a wood screw is given by, say, 800 Newton each. And then we need to determine the distance. The shear force is given by 10.5 kilonewton. So we have determined the maximum permissible longitudinal spacing of S screw. And this is the problem. Okay. So let's simplify the problem. So as I told you, the point is this: the shear flow provided by the screw nail must be greater than the shear flow caused by the shear force V, and then the first moment divided by the second moment of inertia. So make sure that the shear force is already given, 10.5 kilonewton. So I told you several times that it is better to use Newton units for the force. That's why it becomes 500 Newton. Okay? And then can you calculate the second moment of inertia? The second moment of inertia is what? Again, we consider the second moment of inertia for the large cross section. Okay, the large cross section, and then minus, we subtract the second moment of inertia for the negative section. Negative section. In this way, we can calculate the second moment of inertia of this, this rectangular section very easily. For example, for this large section, this is what, 12 times the width is what, 180 plus, and then we need to consider 2 of thickness, that's why 30 millimeters, and the height is given by 200, I don't see that, 280 millimeters third, isn't it right? This is the second moment inertia for this, and the second moment inertia for the negative section is what? Negative section is 12, so you see exactly the same as before, and then 180 times, and the height is what is the height? and then the height is just 100 times 2, so 200, isn't it, right? And third, so we calculate here, we calculate this quantity, we calculate this quantity. Then what's remaining? And also we have the shear force. What is remaining? The first moment, because we are talking about this part, isn't it, right? So let's try to calculate the first moment of this part. The first moment of this part is given by, as I told you, by the mean value theorem, this is nothing but just area times the distance to the centroid. The area is 40 times what? 180 millimeters. And then let's consider distance. Distance is what? Distance is given here, 120. And that is the first moment. So we have all the quantities here, the right hand side. And then let's talk about the left hand side. The left hand side, the shear flow provided by the screw nails is what? So we can calculate it is very easily. So how many screw nails that we have to consider? We have screw nails on left hand side and right hand side, isn't it? So that's why we need to multiply 2. And then the shear resistance, allowable shear resistance of a screw rail is given by 800 Newton. So 800 Newton each. And then those are placed in every s distance divided by s. So let's plug in here, okay? Then we can calculate the distance very easily. Do you have any question? And for detailed calculation using numbers are given in the textbook, you may follow the procedure. So I provide you the concept of these example problems. Here, okay, so how many issues do we have? I want to stop my lecture here today, and we'll cover up to here in the midterm examinations. So we'll talk about the superposition issues later, okay? Do you have any questions? Okay, so let me start my lecture.